Okay, so almost everybody knows that the gamma function can be defined using this integral, and I've derived that on my channel previously in the same series that this video is in. But when people were searching for an extension for the factorial function, this was one thing that they came up with. However, there's another form, and that is this infinite product right here, which was discovered by Euler. So we call it the Euler definition of the gamma function. But they're actually the same thing. You can get from this integral to this product, right? You can prove that they're equal. So that's what I'm going to try to do today. We're going to start with this integral form, and then we're going to try to get to this red product form right here. Okay, so we're going to start by copying down this integral. Now, one thing we're going to do is remember that the exponential function right here can be written as a limit. Okay, so if you recall that, say e to the t could be equal to the limit as, I'm going to use h, approaches infinity of 1 plus 1 over, sorry, not 1, t over h to the h power. Okay, so that's nice and all. If we go ahead and plug in a negative t, where all the t's are, well, we just get a negative t here, or in other words, we can move that down here. So it just becomes 1 minus t over h to the h power. And because you see that, well, they're equal, we can go ahead and plug this straight into the integral. What's even more than that is that we can go ahead and drag the limit out to the outside. And in fact, we can, because you see this upper bound of the integral also goes to infinity, because we already have this limit as h approaches infinity there, we can just write an h there, because either way it's going to go to infinity. Now there's a little more rigor that's necessary to justify this, but at the end it works out to be fine. So the limit as h approaches infinity, we're still going to have the integral from 0. This infinity is, I'm going to replace it with the h, and then we're going to have t to the z minus 1. E to the negative t we replace with this limit right here. We already have the limit expression copied down. I'm just copy down that part. So 1 minus t over h to the h power. And then finally dt. Okay, so now what we can do to simplify this down a little bit more is to make the substitution u equals t over h, where t is the variable, of course. So if we go ahead and isolate t, then we get that t is equal to h times u. And then go ahead and find the differential of either side. The differential of t is just dt. That's pretty basic. So we get dt is equal to, h is a constant, we're going to keep that. And then the differential of u is just du. So this is our substitution right here, okay? Next we have to figure out the bounds. But I'm going to do that right now. So we're going to limit as h approaches infinity. We're going to have to figure out the bounds. So this is t equals 0. When t equals 0, let's just say plug a 0 into here. 0 over h is always going to be 0. So that means when t equals 0, then u equals 0. And similar deal, we do the same thing. When t is equal to h, which is the upper bound, well, we plug it into here. T equals h. H divided by h is going to be 1. So therefore, the upper bound is going to be u equals to 1. So we have 0 to 1. That makes our bounds a lot nicer looking than 0 to h. We have t to the z minus 1, but t is just h times u. Now, we're going to distribute the power of z minus 1 down onto each factor. We're going to distribute it down onto the h and down onto the u. So the h is going to be raised to the z minus first power, and then we're going to have the u factor be raised to the z minus first power. Finally, we have this right here. We're going to copy it down, 1 minus, now t over h, we called that u, so we're going to put that u there, and it's still going to be raised to the h power. Finally, our differential element dt is going to be changed to h du. Now, h, when you multiply h in, notice that you have this factor right here. Multiplying an h in is just going to add 1 to the exponent of this h, because you can combine the powers. If you add 1 to the exponent, just get rid of the negative 1. And then you have h to the z. So that's that h taken care of. Now all we have is the du to write down. And there you go. So that looks much better. In fact, this h to the z right here is independent of our variable of integration u. It's a constant in the u world. That's all I'm trying to say. So we can take this outside of the integral. So I'm going to move h to the z outside of the integral, and the integral bar is going to come in here like that. So now the integral is just this, and that is far simpler than what we had earlier with this. Now there's only one real way that we can intuitively break this down, and that is just to use integration by parts. So we're going to go ahead and set that up and see what that gets us to, and this is going to be a little bit time consuming. Okay, so I just copied the results that we got down up here, and now we're going to apply integration by parts to try to, figure out this part right here. Now, pretty interestingly, this integral right here can actually be expressed using the beta function, which I cover later on in this series, but for now, let's just do integration by parts, and also the beta function isn't really going to help you. So, what do we get? Well, what do we differentiate? We can differentiate u to the, 1 minus u to the h, because h we can treat as a very large integer. So that way, when we differentiate enough times, we eventually get to 0. And then we can go ahead and integrate this other factor, u to the z minus 1. So differentiate 1 minus u to the h, integrate u to the z minus 1. Okay, we start by differentiating this. Let's just use the power rule, right? We drop the power down to the side, we get an h, and then we have this factor repeating. We subtract 1 from the power, so we get h minus 1. And then we have chain rule. So chain rule, we just multiply by the derivative of the inside function, which is 1 minus u. The derivative of 1 minus u is just negative 1. So we're going to multiply that on the side here. And I want you to notice that right here, this negative 1, when you end up multiplying everything out, is going to cancel with this negative sign right here that comes from, the alternating of the integration by parts. So just keep that in mind. When we integrate this, it's also power rule, but just reversed. We add 1 to the power, we get u to the z, and then we divide by the new power, so over z. That's very simple. Okay, next, let's just go through one more example before we generalize a little bit more. Okay, now we have to differentiate this, and it looks a little bit more complicated now, but it's really the same. This negative 1 and this h are both just constants, so we can move them out to the side, okay? Next, we use power rule on this inside bit again. So we're going to have the h minus 1 drop down, and then we're going to have this base, and then we're going to subtract 1 from the power, just like is the standard for power rule. Then we have to multiply by the derivative of the inside again. And the derivative of the inside is once again negative 1. So in fact, right here, we could just do negative 1 squared. So let me get to the pattern in a second. I'm going to do this integration first. Once again, this over z right here is just a constant. We're going to keep that on the side. Pay attention to the u to the z. We apply reverse power rule, so we're going to increase the power by 1. We're going to get u to the z plus 1. Okay, over, I'm going to copy down the z in the denominator. Okay, and then we're going to drop the new power down to the side, and we're going to divide it actually. So right here, I want you guys to notice something before we continue down all the way until we reach 0 for this column. And that's that. Here, you don't really need to worry about the sign. It's always going to be positive because you're just going to keep adding 1. And there's no chain rule necessarily that you need to take into consideration. Here, on the other hand, notice that in the first, third, fifth, etc., you're going to have a positive sign, okay? And this negative 1 right here is going to be to an even power. So basically, these rows all end up being positive because this guy is just a positive 1. This guy, there's no coefficient. And yeah. Now, how about the other rows? So the ones that are in between, okay? Well, you have a negative sign that comes from integration by parts, but you also have a negative 1 that's going to be raised to an odd power. So for this next row, it's going to be negative 1 to the third. For the fifth row, it's going to be negative 1 to the fifth, okay? And that's going to cancel out with this negative that's going to accompany it. So in actuality, these middle rows are also going to be a positive sign. You can, in essence, cancel this with that. And same deal with here, right? You can just get rid of this. Okay, so all of these are basically just going to be positive, okay? And that makes it a lot simpler for us because we know they're all going to be positive. Okay, so let's move on. As we keep going, let's go to the iteration where we differentiate, let's say, h minus 2 times, okay? So just to solidify this pattern in our head, when you differentiate x to the n times, right, with power rule, what do you get? You're gonna say n is equal to 3, okay? You differentiate x to the 3 times. You get 3x squared, then you get 6x, then you get just 6. You're gonna get to the constant. So in order to get to 0, you have to differentiate 3 plus 1 times, okay? So that's 1, 2, 3, and then 4. So similarly here, we have to differentiate h plus 1 times to get to 0. Now right here, I'm no longer going to write this as alternating. We know that these are all going to eventually become positive. I'm going to keep putting down plus signs. Okay, so let's go to the h minus second iteration of this, okay? So this h times h minus 1, you notice that it's going to go on to h minus 2, h minus 3, and so on until you get closer and closer to 0. So h times h minus 1, we're going to put a dot, dot, dot. Okay, so when you differentiate 1 time, this is minus 1. When you differentiate 2 times, this is minus 2. So when you differentiate h minus 2 times, well, the power is going to be h minus 2, which is just going to be positive 2, okay? So the new power is going to be positive 2. So the coefficient is going to be 3, and then the power is going to be positive 2. And it's going to look like that. You can work that out by yourself if you need to. Okay, and I'm going to keep differentiating until we get to 0. So this right here is just h factorial, okay? So keep that in mind. Okay, next, let's work on the integration column. Integrating. When you integrate 1 time, the power is gonna go to z, it's gonna be z minus 1 plus however many times you integrated, right? So right here it's gonna be plus 1, here it's gonna be z minus 1 plus 2. Okay, so if we're going to go to the h minus second iteration, just like we did here, okay, that's what this row is, then what you're going to get is z minus 1 plus h minus 2, okay? Okay, so the new power is going to be u to the power of this guy. So I'm going to simplify that a little bit. We're going to get z plus h, and then minus 3. I think that is correct. Okay, that is correct. So and then we have to deal with the coefficients. So we have the z times z plus 1 and so on. Okay, I'm going to copy that down right here. So z plus 1, z plus 2, z plus 3, until eventually we get to, well, when we integrate something and it gets to here, we're going to, at this step right here, it's according to reverse power rule, we're going to divide by the new power. Okay, we're always going to divide by the new power. So therefore, the power should climb all the way up until this right here, z plus h minus 3. And yeah, that's this iteration. And okay, now it gets simpler because we can just integrate again and again. This right here is associated with that, this with that, and this with that. Okay, we're going to go for one more iteration. When we differentiate this right here, h factorial is just a constant. Remember, our variable for, the variable for integration we were working with is u. There's no more u here, so when we differentiate it, well, just differentiate a constant, you're going to get 0. This right here, on the other hand, is not going to be 0. We're going to just integrate it one more time. We add 1 to the power, so we get u to the power of z plus h. Then we divide by all of these coefficients, which we already had. And it's going to go all the way up until, well, we're going to divide by the new power, so it's going to go all the way up until z plus h. Okay, So I hope you can read that. If it's too small, I'm sorry. So now we're going to write this out using the rules for the DI method. Okay, I just copied down our entire integration by parts thing one more time, so it's a little smaller, but hopefully it's easier to read now, okay? I'm gonna get rid of these positive signs because I'm pretty sure we know that already. Now, when you do the DI method, the guideline is to multiply diagonals, okay? So we're gonna get that, we're gonna get something multiplying this, we're gonna get these two multiplying h factorial multiplying that, and then we integrate this final row. But this final row has a factor of 0, and when you integrate 0, well, you're gonna get 0. So we're gonna just ignore that and multiply all the terms instead. So this is gonna be kind of difficult. Let's write out just a couple from the top and then a couple from the bottom, and we can eventually observe a pattern that makes it a lot easier than it seems. Okay, so that's the first couple of terms. Now let's just write down this second to last term and this last term right here. So eventually we're going to get down to okay, so that's what we get, and let's go ahead and try plugging in bounds, okay? Now, when we plug in u equals 0, all of these terms have this u to the power in it. So you have u to the z plus 1, so on until you get to u to the z plus h minus 1, and finally u to the z plus h. And that just means that this term, this factor right here of u to the power, when you plug in 0, it's always just going to go to 0. So when you plug in u equals 0 for this entire expression right here, you're just going to get 0. All of the terms are going to get zeroed out by this one factor up here. So in essence, all we need to do is just plug in a 1 into u. Except when we do that, notice that this term right here, there's a 1 minus u. So when you plug in a 1, this is going to get zeroed out. Same deal with this one and the rest of them, right? Here you still have the 1 minus u, except for the last one. The last one is the only term that doesn't have this 1 minus u that zeroes out, its value. So when you plug in 1, all of these terms are going to go away. So they're all going to go to 0, except for this last one. So this last one, what's going to happen is once you plug in u equals 1, this entire term right here is just going to go to 1, because 1 to any power is just 1. You're going to be left with this h factorial over z times z plus 1, and so on until z plus h. And that's pretty elegant. So that's going to be an important form that we're going to work with in just a second. Okay, so we saw that after performing an integration by parts, we're left with this right here. I'm going to move this h to the z up here. So we're going to have h factorial times h to the z over all of this stuff right here. And this is actually going to be quite important for the next video I'm going to do. And that's putting it also into a product form, but into something slightly different. So yeah, I'll be referring back to this in the next video. Now, what we want to do is we start writing everything here as an infinite product, because we're getting closer and closer to this form. First of all, notice that we have this 1 over z already that you see hanging out the side here. Let's just take it outside of the limit. What we get is we're going to drag the 1 over z. Okay, we're going to have the limit as h approaches infinity. Okay, now inside of here, notice that our final product is an infinite product. Okay, so what we want to do is we're going to find a way to rewrite the inside as an infinite product. Or, in other words, a product with h terms, or h factors, because h is going to approach infinity at the end either way. Okay, let's do that. Let's take care of the easy part first. This h factorial and these factors on the bottom, they all have h terms, right? This starts at 1, goes to 2, so on until it reaches h. So there's h terms in the bottom. And h factorial also has h factors because, it's 1 times 2 times 3. It just counts up until it reaches h. That's pretty self-explanatory. So let's write this out. We're going to pair the 1 and the z plus 1 together. This 1 comes from the h factorial. This 2 is the second factor of the h factorial. And then this z plus 2 is the second factor of the denominator. Okay, and you can see where this is going. We're going to keep multiplying on. All right, let's go to the end terms. We're going to have h minus 1, which is the second to last term of the h factorial. And then we're going to have z plus h minus 1, which is the second to last factor of the bottom. Okay, and then we're going to have the final term, which is just h. And in the bottom, that would just be z plus h. So you can see that all of these things in the denominator, you can multiply that together to get what was originally here. And the top, I keep writing my h's like n's. When you multiply all the numerators together, you get h factorial. All right, but we're missing one part, and that's this h to the z right here. Okay, so up here in our finished result, in our end result that we're targeting, notice that this z power is going to stay. Okay, so maybe that kind of matches up with this h to the z right here. So if the z power is going to stay, maybe what we really have to do is just find a way to express h as an infinite product. And that is quite easy. So we're going to write this here. H, if we want to make it an infinite product, why don't we make it simple for ourselves? Let's make it telescope down to just h. And okay, here's what I mean by that. We're going to start with 2 over 1, then we're going to multiply on 3 over 2. Okay, you see what's going on? 4 over 3. Basically what's going on is the numerator of this one cancels the denominator of that one. The numerator of this one cancels the denominator of that one. And that's going to keep going. All right, and we're going to have h terms. So let's write down the term with the h on the top. Okay, and the bottom is going to be 1 less than the top. So it's going to keep canceling. Okay, h minus 1 is going to cancel with h minus 1. And this is exactly h. All right, so let's go ahead and just write this on next door. Okay, and by the way, here there's the h to the z, so identically right here, I'm going to raise everything to the z power. But notice when you raise this whole expression to the z power, it's just a bunch of things multiplying together. So by a power property, the power is going to apply to each of these factors. Okay, so and that makes life easier for all of us. We're going to have 2 over 1 to the z. Then we're going to have 3 over 2 to the z. Then we're going to have 4 over 3 to the z. Okay, and then so on until we reach h over h minus 1 to the z. So there we go. That is our limit, but expressed as an infinite product. Okay, now this is the n equals 1 term. This is the n equals 1 term. Okay, so we're going to try to group these guys together. And we're going to try to group these guys together. Okay, because this is n equals 2, this is n equals 2. But notice that there's a slight problem here. In this bottom row right here, we start at 2 and count to h. Okay, so there's h minus 1 factors. In the top, we start at 1 and count to h. So there's h factors. So this guy is actually going to be paired with this, okay? This is the h minus first term. This is also the h minus first term. So what about this final guy right here? Well, we have to find a way to also pair that up with something, right? So let's multiply something on to this bottom row that matches this pattern. That'll be able to pair up with this guy up top here. So I'm gonna write the paired ones right now. H approaches infinity. I'm gonna write these guys together, okay? Okay, so these are all the terms that we have paired up. Now let's deal with this left over right here. H over h z plus h. Now the obvious way to do it, well, here we have h over h minus 1. Why don't we just continue the pattern and add 1 both to the top and the bottom? Right, we're going to get h plus 1 over h, and then to the zth power. So that way, now it's also going to match this pattern that's going on here, okay? You can see that right here, the term inside of the z is 1 bigger than the term out. The term inside of the z is 1 bigger than the term outside. And same deal goes on right here. And see, the denominator also matches a pattern that we see going on in all of these existing factors. But the problem is, now that we introduce that, we have to find a way to, also negate it. So that way the value stays the same. You can't just multiply something and expect everything to be equal. Okay. So what we're going to do is multiply by its multiplicative inverse. And that's just the same thing, but with a negative power. So we're going to multiply on it h plus 1 over h to the negative z. Okay, so these two, when they combine, they're going to multiply out to 1. And multiplying a 1 to your product is not going to do anything to it. So the value is now going to stay the same. All right, that's pretty obvious. But how do we deal with that? This right here, we can already figure out how to write in terms of this infinite product. But we have this extraneous guy just hanging out here. Well, remember that if you take the limit of a product, we can take the limit of each of the individual factors first, and then combine them at the end to get the same result. How do we apply that to our case? Well, the first limit can just stop here. Let's have another limit that's identical applied to this second guy. Okay, h approaches infinity. And we can agree that makes sense because the limit kind of distributes onto each of these factors. Hey, what is this guy? If you plug in, as this goes to infinity, if you expand this out right here, so let's split the fraction up. So we're going to get over h, okay? H over h is just 1. Okay, so we just put it in a different form. As h approaches infinity, notice that the second term right here is going to go to 0. So we're going to be left with a 1 to the power of negative z. 1 to the power of anything is just 1. So in fact, this right here evaluates to 1. And that's really nice, because that means we no longer have anything else on the outside we need to deal with, okay? Because when you multiply 1 to something, the value stays the same. So right here, this is what we now have. All right. And like I said earlier, now we know we can write it in terms of an infinite product. So 1 over z, we're going to limit as h approaches infinity. The product, all right, that's a very tall product. We're going to start with n equals 1. Okay, this is going to be the n equals 1 term, n equals 2 term. All right, it's going to go on until we reach the n equals h term. So we're going to start at n equals 1, and it's going to go all the way up to h. And these look kind of similar. Let's use, well, yeah, okay, let's just stick with n for now. Okay, let's just recognize the structure of each one of these factors, and then we can put that down here. So the first term has a 1, the second term has a 2, and then the h minus first term has a h minus 1, and the h term, it has a h. So that's going to iterate, okay? So up here, we're going to have an n, and then the same deal is going to happen with this other number that's being added in the denominator. So right here in the first term, it's going to be a 1. Right here in the second term, it's going to be a 2, and so on until we reach the h term. So this is going to be z is going to stay, and then plus n. So that's going to iterate. All right, now let's work on the second factor. The second factor is going to be, notice that this number in the numerator is always going to be 1 greater than your current term. So if you're in the first term, it's going to be a 2. If you're in the second term, it's going to be a 3. So it's going to be n plus 1. It's 1 greater. And the bottom is just going to match n. All right, and then it's raised to the zth power. So now we have it in a nice infinite product form. Let's go ahead and manipulate this slightly to simplify it and make it look like this. Okay, pretty obviously what I did was I copied this down up here. And now we're just going to make a final few very minor manipulations to make them look the same. Okay, this and the red, which is our target form. So the 1 over z is going to stay for all the steps. Now, a shorthand that we like to use is just to put an infinity up here. It means the same thing as the limit. So we're going to, instead of having a limit, we're just going to put an infinity up there. And I'm pretty sure we're all familiar with this notation. Okay, it's going to be infinity. All right, here, notice that in the numerator, you have this 1 plus 1 over n to the z. So we're going to keep the zth power factor up in the top. Okay. Now, we're going to flip this down into the denominator. How do we do that? Well, This might be pretty obvious for some of you, but basically what we're going to do is multiply by its reciprocal. So z plus n over n, and we're going to also multiply a z plus n over n in the bottom. Like that. Okay. Now notice the top is going to entirely cancel out to 1, so you're now dividing by its reciprocal. Very simple, let's do that here. Divide by its reciprocal, z plus n over n. Okay, and finally, notice that here, it's not a combined fraction, instead they split it into 2, so we're going to do that too. When you distribute this divided by n into both terms, let me copy this down first, math the product, going from n equals 1 to infinity. Okay, up here, when you split up the fraction, n over n is just going to be 1, and then you're going to just be left with 1 over n for your other term, to the zth power. Okay, and we're going to do the same thing in the bottom. This n over n, when you split it up, it's going to be 1. In fact, you don't need parentheses here. And then this z over n is just going to stay. Okay, now these match. And yeah, that's how we prove that the gamma function's integral form is equivalent to its Euler definition or Euler form. So we just did that. All right.